Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. Again, Lord, I thank you for these students. I just pray that you'd help us to use this time wisely, Lord, to just review any questions that still remain about integration and numerical integration. I just pray the students also would just have the presence of mind to ask questions which are helpful as they study for the test, which is upcoming, and just pray that they would be able to draw their thinking together a little bit more today, Lord. In your name I pray. Amen. All right, let me, before I take any fresh questions, let me dispense with the discussion I had earlier. Well, I suppose I seem to have accidentally worked one of your homework problems over here. Sorry about that. I forget which one this was. It's 1 over 2 plus sine x is a little bit, we already did this one yesterday. I mean, make that go away. We don't need to be distracted by that. You guys have already done that one. That was yesterday. We already talked about that yesterday. Make that go away. So, dx over 2 plus sine x is clearly a nice candidate for a Weierstrass substitution solution. So here's the beast right there. And so we put dx is 2 to u over 1 plus u squared. 2 is 2. Sine x is 2u over 1 plus u squared. And so then we clear out the denominator, multiplying the top and the bottom by 1 plus u squared, as we did. All right. It's important for me to go back over these steps because we know if I made a mistake, there's really no guarantee. It would have been pointed out to me earlier. Although they made a couple corrections this morning. I got to give it to them. They're getting better. We'll see who wins next Tuesday, though. That's the moment of truth. All right, so as you guys know, we have some classroom interaction scheduled for next Tuesday. The highest form of classroom interaction, the test. Let's see here. U squared plus u plus 1. I like tests. It makes me feel like I'm not just talking to myself. It's helpful to me. You know, I like my job. There's like no other place that I could just talk to people about math for an hour and they would listen to me. So not only do you listen to me, like they even pay me money to do this. It's amazing. You know what happens if you just go talk to random people on the street about math? They walk away. They walk away. They won't let you. They might insult you, call you various things. Nerd, geek, weirdo, etc. Anyway, here we go. So after the Weierstrass substitution is done, we find ourselves faced with du over u squared plus u plus 1. You notice the 2 is canceled. Right? Now that's an irreducible quadratic, so I got to complete the square to come to terms with how to integrate it. This is u squared plus u plus 1, which is u plus 1/2 squared. That leaves me 3/4. Of course, 3/4 is the same as square root of 3 over 2 squared. Right? So this suggests to me a trig substitution of u plus 1/2 equals to square root 3 over 2 tangent theta. The reason I make that substitution is that then u plus 1/2 squared plus square root 3 over 2 squared will be basically 3/4 tangent squared plus 3/4. In other words, it's 3/4 times tangent squared plus 1, but tangent squared plus 1 is secant squared theta. So it simplifies like that. Usual tangent trig substitution. So anyway, we get secant squared over secant squared, cancel, and then you unwrap the substitution, and there you go. It's a lot like the cosine integral we did yesterday, but the wrinkle is, of course, that we didn't end up with something real easy after the Weierstrass substitution. We still had to think a little bit. Any questions about this? Ooh, chapter 9, some differential equations. That's really interesting. Those are fun. No, I'm not allowed. I'm not allowed. I should wait until after the test. Let's see here. You guys get annoyed if I lecture on stuff that you're not going to be tested on yet, right? Yeah. Any questions? All right. Yes, sir. Oh, I was asking about this. I will take further questions. I'm sorry. I miscommunicated my questions. Let me finish talking about these, then I'll take your question. Yes, sir.
That one right there, I see that the 2's canceled out. But the question I have to ask is, what about the 2u at the bottom? Where does that go?
Well, so I can divide the top and the bottom by 2. So that cancels the 2 here. And when I divide by 2, a fraction, that it gets rid of both 2's, right? Because, this is 2 du over 2 times 1 plus u squared plus u. So these 2's cancel. Yes, sir?
Can you tell me again how you got plus 1/2 equals 3/2?
Yeah, well, I have the sum of things that are squared. So I know that if I do this, it makes the substitution match up with that other term, so I can factor out the constant. So basically, I want to make that become this number times tangent squared theta, because I know tangent squared theta plus 1 is secant squared theta. So the squared 3 over 2 has to go here because of that one. But I guess the shorter answer is it's the trig substitution. All right, let me talk about these numerical section 8.7 problems just a little bit. I try not to talk too long about them. But the number 21, it's a little bit harder than what I showed you guys yesterday. So number 21, well, I don't know, maybe it's about the same difficulty, it's just kind of a little bit different. E to the minus x squared dx from 0 to 2. You're supposed to find what n do we need for this to be less than 0.01. I'm just going to discuss the trapezoid rule error. There is not a unique correct answer to this problem. There's a whole range of possibly correct answers, all right? So that's a little bit different from our usual experience. But the basic thing is here, if I want to make the error 0.0001, I know that the error is governed for the trapezoid rule by this estimate, right? So like the error in the nth trapezoid rule is less than b minus a cubed times some bound on the second derivative divided by 12n squared. All right, so the only thing that I really don't know just from looking at the problem to start with is this m. We have to figure out what's the bound on the second derivative. So how do you do that? Well, I start with my integrand, e to the minus x squared. I differentiate it, right? Then the second derivative involves product rule. This stuff over here doesn't matter. I was just factoring for the sake of factoring. After the dust settles, I didn't even use that. If you don't mind, I'm going to erase it. It doesn't hurt us to erase it, but you could factor it like that. And then I take a third derivative. I didn't even actually use the third derivative either. I won't erase it because some of you, well, those of you who do this homework problem, for Simpson's rule, this m is different, right? This big M for Simpson's rule needs to bound the fourth derivative. I'm just showing you how to find the m to bound the second derivative, okay? So to get your pause on Simpson's rule, you need to differentiate again, right? You'll need to differentiate one more time to get the fourth derivative. All right. So I'll just leave this here for your convenience. All right, so focus. I want to find m such that the second derivative is less than m for x taken from the integration region, which is 0 to 2. So here it is. We're looking at the absolute value of f prime prime of x. This is the absolute value of 4 times the exponential times x squared minus 2, right? X squared minus a half. Everybody with me? All right. So properties of absolute value that are important. The absolute value of a product is the product of the absolute values. It's multiplicative. It's a precious, wonderful fact about the absolute value function. It's very special. This only happens for the reals, the complexes, and the quaternions. Anyway, so we get 4 times this times that. So you got a product of 4 positive things. How can you make that, if I want to make that as large as it can possibly be for given variables, I just need to choose each one of those as being as large as they can be, right? So 4 is 4. e to the minus x squared. What's the largest that can be going from 0 to 2?
0.
No. 1. Now the reason, here's a part of the reason we know that, if you didn't see it from just more basic logic. So the first derivative of f is minus 2x e to the minus x squared, right? Here's the sign chart for the first derivative, right? That shows that this function is increasing for negative x and it's decreasing for positive x, right? So if a function is decreasing from 0 to 2, the largest value it takes is at the left endpoint. But on the other hand, of course, you could just argue directly, if I'm looking at the exponential of minus x squared for x positive, well, I mean, minus x squared is always negative, right? So if you have the exponential of a negative argument, the largest it can possibly be is when that argument is actually 0, right on the edge of being negative. So that's e to the 0, which is 1. So the largest e to the minus x squared can be as 1. I'm not sure if you really need calculus to show that. I mean, anyway, common sense or calculus shows you that that's 1. And then x squared minus a half, again, I don't really think I need calculus for that. I just need some kind of basic, I mean, the intermediate value theorem is at play here, fine. But if I think about x squared minus a half from 0 to 2, I'm looking at just this part of the graph of x squared minus a half, right? And if you think about that, what's the maximum output from that? Well, it's this 7/2, right? So if I replace this with 7/2, certainly this is true. Could you do better than my estimates? Yeah, probably. Pretty sure you could. But here's a way. So I get m of 14, right? Now that I figured that out, that's the hard part. I go and I set the error in the trapezoid rule equal to 0.0001. So I got my m is 14, 2 minus 0 cubed divided by 12n squared. It's all for n squared. N squared gives me 8 times 14. 8 is the 2 cubed. 8 times 14 divided by 12 times 0.001, right? And you take that, you calculate it, you take the square root, you get 305.5. As we talked about yesterday, you can't take 0.5 iterations of the, you can't do a trapezoid rule for 0.5 sub-intervals. You got to go to the next one. So 306 is the answer I get. Now, what does the book say? The book says that n is greater than or equal to 78. You're like, well, your answer is wrong. No, my answer is just not optimal, right? In fact, my choice of m probably could be improved through better inequality arguments. I don't care. I'm just looking for a logically correct answer, and the same for you guys. So if you don't get the book's answer, but you get something that's within reason of the book's answer, you're still fine. Does that seem fair? Yeah.
What constitutes within reason?
Is it logically included in the book's answer? The book says n greater than or equal to 78.
Okay.
So I say n greater than or equal to 306. So I'm, again, it's within the context of the book's answer, but the book has found a way to get a tighter bound on the second derivative is what this boils down to. It's fine. I'm not being that clever. You can also be naive like me. What's that?
Is that 1 million?
Did you get this? Why did you get this, or?
I'm just saying. Like,
Oh, you got a million?
It's a greater than.
Oh, right. What I told, I said this kind of thinking is only really good for your Calculus 2 homework. If you try to employ this kind of thinking as it applies to regular inequality arguments in your daily life, it may not work. For example, if you're a construction contractor and you tell the city, I can finish construction on that intersection in no more than 100 years. They're probably going to laugh you out of the room and say, that's nice, go away, right? It's what?
It is faster than the last guy who worked on it.
Yeah. Yeah, really. it's probably more important that you get a tight bound for that kind of question. Like, well, I can do it in at most 6 months. I can do it in less than 6 months, right? That would be. But it kind of depends on the thing. The thing is here. This is homework. I don't want to make it into a job, so I will allow you relatively naive arguments about the bound. All right. If you were more careful, you could do better. Now, this next problem, 31, is quite beastly. See, because here you're asked to use n equals 20 Simpson's rule to estimate the theoretical error. So the nasty thing about this problem is basically it's saying you have to find a bound on the fourth derivative of this function. Oh, ouch. Ouch, ouch, ouch. That is not fun to directly differentiate 4 times. Right? It's the quotient rule upon the quotient rule upon the quotient rule. It's quotient rules all the way down. Now, you are free to use Wolfram Alpha, Mathematica, whatever floats your boat to do this differentiation, okay? Out pops the fourth derivative. This is not it. This is numbers I made up for the purposes of this illustration, okay? That's not the fourth derivative. And if you simplify it, it simplifies to the fifth because there's like a common x squared plus 9 upstairs. If you don't simplify it, you'd have x to the sixth. It doesn't really matter to me, okay? Now, once you do that, though, you have to find a bound on this expression. How do you do it? That is what I would like you to understand, even at least the naive way. Again, same logic as we talked about last time. If I want to make the fraction smaller, right, I make the what? I make the numerator. If I want to replace the fraction with something that's larger than the fraction, right, what do? I make the denominator as small as I possibly can, right, and I replace the numerator with something that's larger than what's here. Yes?
So how does that work if you can choose different x's for the same output?
What do you mean?
When you're going to choose a different x value, you're going to find one x value that makes the denominator.
Well, yeah, I'm trying to find a number that applies for this whole range of things, right? So I basically have to look at. I'm just saying you can look at worst case scenarios for the numerator and the denominator separately. You can divide and conquer. So if I look at the denominator, clearly the smallest that can possibly be going from 1 to 5 is 10, the inside, right? So 10 to the fifth, that's basically the smallest that this 10th order polynomial can be.
So
1 to 5.
You're using a 1 for x, right? You replace
Yes.
it with a 1. So wouldn't you have to do that on the top too?
No, like I said, I'm dividing and conquer. I'm saying, and this is why I don't get an optimal bound. Right? If I insist on using the same x for the whole argument, I will do better. Because the optimal bound is somewhere where you're at the same time above the top, but at the same time, you're trying to make both the numerator large and larger than the expression and the denominator smaller than the expression such that the ratio is larger than the... Yes, you'd have to think, that's essentially why I don't get the strict bound is because I'm thinking about different x for the top. I'm dividing and conquering. I'm thinking about the numerator separately. But as long as I come up with a statement which is true for all x, I'm okay. It is true that for all x, the absolute value of the numerator divided by 10 to the fifth is, larger than the given fraction. So if you want to, I could write this 2 steps. The first step is this. Then the second step, and this is less than or equal to that. So it's just. But the numerator, I put into submission using the so-called triangle inequality. So the triangle inequality says that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And the same thing holds for more things. This is super useful because then I can replace this hard to think about thing with this very easy to think about thing, right? 16,672 times the absolute value of x to the fifth. And then if you think about absolute value of x between 1 and 5, of course, 5 is the largest it can be, right? And there you go. That's it. That's a way to find an am. Partly for the reasons he's talking about, I'm sure it won't be optimal, but it should at least give you an answer which is consistent with the book's answer, which is all I want. All right, I have now spent entirely too much time talking about section 8.7 today. Let us talk about integration, which is the majority of the test. This is like maybe 5 to 10% of the test at the most, right? I know it's hard, this idea. But. Oh, by the way, I do not expect you, there's many things I expect you to remember, but these two things are not one of those. This I would actually quote for you on the test for your purposes, all right? So those theorems I do not expect you to memorize. I do expect you to know the Weierstrass substitution and perhaps the hyperbolic Weierstrass substitution. I probably would, I don't really expect you to memorize the hyperbolic one. I might ask you to derive it though, so. But the trig one, I think it would be wise to have that on the list of things that you know. It's just very useful. All right, finally, your question. Yeah, you had a question. I did.
But that problem over there, first one that you talked to us about,
Oh.
which problem was that? Because there's one that's similar.
Oh, the 1 over 2 plus sine x?
Yeah.
Well, I just assumed it was one that was in the homework set because I haven't actually checked that, but they told me it, they asked me it, and they didn't tell me which problem it was earlier, so I don't know. Can somebody help him?
I don't know if I misread it, but 2.6 number 25, it's dx over 1 plus sine x,
Oh,
and that seemed to be like a bit more tricky. Because
really?
you couldn't, it ended up being an even, it ended up going out to 2 over u plus 1 plenty squared, and then like, it got me a different answer than like what that seems.
Well, no, yeah, that's a different problem. It would not be the same. Let's see here.
I just,
Number, which was it?
number 25.
Yeah, the one I just was looking at. Hey. Well, 25 is 2 plus sine x.
Then I'm probably different.
Hopefully we're every so often a book has multiple printings. I hope we're not dealing with that issue. Yeah, for me 25 is 1 over 2 plus sine x. Let's see, I assigned 23, 25, 29, 37. 23, 25, 29, 37. Yeah,
Alright, that's cool. I probably just misread it.
no problem. So other questions? Well, all right. I'll let you guys think. I'm going to do the integral of secant cubed per your request. This was requested of me yesterday. I didn't get to it. Now, I'm a little trepidatious to do this because I'm afraid that what we're going to find out is that the Weierstrass substitution isn't all that. And that would make me sad. So I'm cautiously optimistic about what we're about to do. See how it goes. We're still dealing with 1 over a cube, and that's probably what's going to be beastly. Or it could be worse, I don't know. So this is what? This is the integral of d theta over cosine cubed theta. Oh. I think I just realized the cost of the Weierstrass substitution. So now theta is what? So I'm saying x is equal to, replace the x's with thetas here, right? Right? So making a u equals tangent theta over 2 substitution. This is what? This is 2 du over 1 plus u squared, and then cosine cubed, which is what? Yeah. Okay. I mean, there is a general principle, which is there's some sort of, and this isn't always the case, but a lot of times it's hard to escape this principle, which is that there's some sort of conservation of difficulty in integration. Now, that's not generally true. I can show you ways to make easy problems very hard. I can do that. So that principle is not generally always not violated, but generically speaking, it's kind of a good rule of thumb. And we know that the integral of secant cubed is unpleasant using the techniques before we got to trig substitution and all that. We had to integrate by parts, and it looped back. And it's still, we need to know the integral of secant theta to do it last time we did it. It wasn't easy. But maybe, just maybe, this isn't too bad. I don't know. Let's find out here. Oh. And how many u's? So I guess you got a 1 plus u squared upstairs, right? Squared, right? Huh. So this is the integral of 2 times 1 plus u squared du over 1 minus u cubed times 1 plus u cubed. Do we need to do long division, or are we already good to go? Yes, sir.
Why is 1 plus u squared second power downstairs?
Well, you could think of it this way. If I bring this downstairs, then I would have 1 over 1 plus u squared cubed, and then a 1 over plus u squared, which is then 1 over, but that's happening in the denominator, so I don't know. However you want to see it.
Why did you bring it back down on the denominator in the last one?
Like I said, that's one way you could think of it. I mean, here, I'll think of it a different way, just a second. So we've got 2 over 1 plus u squared, big parentheses, 1 minus u squared cubed, divided by 1 plus u squared cubed. So I can multiply this by u squared plus 1 over u squared plus 1. Some of you will like this more. So that gives me 2 over 1 minus u squared cubed, divided by 1 plus u squared squared, which is 2 times 1 plus u squared squared, divided by 1 minus u squared cubed, which of course is what we have here. What's the partial fractions decomposition for this?
Where did you get the 1 plus u cubed and the denominator?
Oh, well, 1 minus u squared is 1 plus u times 1 minus u, right? So if I cube that, I get those. So I've got this monstrosity here. 2 times 1 plus u squared squared divided by 1 minus u quantity cubed. Did that answer your question, or? Okay. And the partial fractions decomposition for this is not too bad, I guess. It's a over 1 minus u plus b over 1 minus u squared plus c over 1 minus u cubed plus d over 1 plus u plus e over 1 minus 1 plus u squared plus f over 1 plus u cubed So you can do it, right? Multiply by the denominator, we get what? It's like this mathematical analog of like that cliffhanger on the Ninja Warrior. Like after you're done with this one, you gotta like shake it out. Get ready for the next one. Sorry, you may not know what I'm talking about. It's okay. I like the Ninja Warrior show. They compete and compete and compete and compete and never win any money. It's kind of funny. It's like, what if we made a game show where the thing you want to win is so impossible to win that no one ever wins? Except like every about 4 years, somebody wins. But they're like, I'm going to quit my job. I'm going to win that $500,000. It's poor souls quitting their job to run around their backyard. I know, right? What they should do is try to like think of a regular job where they could make it into the Ninja Warrior thing, like garbage collection, for example. Would be a good thing. Be like, I'm going to collect the garbage like a ninja. And then you just try to work the obstacles in, you know, like maybe you build a salmon ladder on the side of the truck or something. I don't know, and so forth and so on. Yeah. Yeah, I don't know. Pac-Man, so we feed Pac-Man. I'm not sure I want to really do this. So Pac-Man, although we get two things pretty easy, 1 and -1, that gives us what? Eight. This is also 8. Now 1 is killing this, and this. The only thing that remains is that one, which is 8c. C is equal to 1. -1 kills everything on the right-hand side. Here, 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 here. This is the only thing that lives. So minus a minus 1 gives me 2. You get 8f. F equals to 1. Well, 1 minus a minus 1 is 2. 2 cubed is 8. What's that? This is the part where we differentiate the equation. And we're happy that we didn't multiply this out because we can do the chain rule. So Pac-Man prime would be 4 times 1 plus u squared times 2u equals to, oh. Okay, I'm tired. I can't. I don't want to subject you to seeing this, but it's clear how to finish. I mean, so to finish it, I would differentiate. You have to do the product rule, right? But then when you finish that, when you feed 1 and -1 into the derivative, it's still pretty simple. You just get, you'll pick up what last time we picked up f and c. When we evaluate the derivative, we'll pick up e and b. like that. We'll get values for that. And then the next step, we'll get a and d after we look at the second derivative. And then you'd have that as a linear combination of things you can integrate, and then out pops the integral of secant cubed. But yes, it's a way, right? Like I said, this Weierstrass substitution is a sledgehammer, and it'll knock it apart. The trouble is putting it back together could require some work. So I think we find that the integral of secant cubed we found previously is still the best way, without doing more. So tell you what, I'll tell you what the answer is. Well, if I could just use the formula, there'd be no point in doing any of this. Let's see here. What do you mean use the formula? 1 plus x squared. I'm not sure what you mean by that. You mean we already worked it out, so we don't need to work it out again? I mean, I hear what you're saying. So 1 minus. Come on, Wolfram Alpha. Don't let me down. I think I needed to give it some guidance. Expand. Yowzers. Great googly moogly. What on earth? Come on. It knows too much. It was 1 plus x squared squared, right? 1 plus x squared squared divided by 1 minus x squared cubed, right? Yeah. Stupid thing. It's what's that? Yeah, I put the 2 times 2, right? Let me try. It is doing other things than partial fractions. Let me try partial fractions for that. Oh, there is a oh, there it is. There is a partial fractions. If you have trouble, sometimes it's hard to get Wolfram Alpha to do what you want it to. Engineering student showed me another website that was pretty good for partial fractions. Oh, that's annoying. Covered up what I wanted to compare to. I just found that, oh, I think you guys are right about a sign. I made a sign error. If I believe what I'm, oh, sorry, age old. HDMI problem. Okay, there we go. I must have missed a sign somewhere on that one, just like you guys are trying to tell me. I'm not sure what I did. I'd like to tell you, but it's behind the screen. So we found that one, and we found one over here, which means I made a mistake somewhere. Oh, no, I didn't. No, I didn't. Here's the difference. Mine is 1 minus u cubed. So this is the same. Since I was using 1 minus u instead of u minus 1, I did it with x, but I don't know, I could put u here. Would that be helpful? No, doesn't matter. So apparently the other ones are minus a half, minus a half, minus a half, and 1. Well, you know. Yeah. What's that? Well, those are squares, though, so like 1 minus x squared is the same as, these ones will be different. The squared terms, that is actually the value, but you're right. For Well, A would be a half. I don't know. A would be minus a half. D would have been a half. And B and E, minus a half and minus a half. But anyway, as you can see, this would be a reasonable question for a take-home test or something, but probably not for an in-class one, right? At least not the completion of this argument. So secant cubed, on the other hand, you could still do on the test, but you would have to use the method we used in lecture earlier, right? So even so, that would be one of the harder test questions that I would ask. Yeah. Okay, anyway, enough about that. Any questions about other things? Let me erase the evidence. Yes, sir. Yeah, I mean, there's a time and a place for a Weierstrass substitution. So quite clearly, something like this, or the other problem, pretty much any of the problems that you see in the homework for the section 8.6, those are kind of target examples. Here's a place not to do it, right? You're like, oh, tangent of x dx. Wait a minute, that's sine of x dx over cosine of x. And you're like, aha! That is a rational function in sine and cosine. I can use the Weierstrass substitution. This would be an example of a wrong application. Because, of course, this we should go back to what we already know, which is that's like minus du over u, right? So, it doesn't really... As a rule of thumb, if we've already found some solution in our previous work, it's probably not the case that the Weierstrass substitution is easier. It's a weapon of last resort. It's Marshall law for integrals. I don't know. Yeah.
Question on the test, I'm not sure if you might already asked it, but would you tell us which type of technique of inquiry
No.
you use?
No. Not generally speaking. You have integrals, you do them. It's up to you which how. Now, since you guys are so nice, I may have a couple of problems. There will be some on the test which are just not guided. It's just an integral, do it. There are other ones where I might say, use the Weierstrass substitution, or use partial fractions, or something like that. What's that?
I guess I do it this way because I want to see it.
Yes. You're like, but sometimes I don't want advice on how to do it. Yeah, I know. So either kind of question is possible. But yeah, there probably will be some on the test where I say use integration by parts twice to calculate something, or whatever. But I try to stay away from too much descriptive how to do it, because then invariably there will be somebody who doesn't quite understand what I'm saying in words, and that creates other problems. So I try to be very careful with hints. In retrospect, hints have been very hurtful sometimes when I was trying to be helpful. So hints are a dangerous thing on tests for me. Other questions? Earlier section asked if they had a note card. The answer is no. No. Yep.
I just want to make sure I'm doing it right for the numerical integration and calculating error. To find out the largest value.
Mm-hmm.
If it's just if it's not a numerator denominator thing, it's fourth derivative of d to the negative x squared. Can if we separate it out into 16x to the fourth plus minus blah blah blah, and then all times negative x squared. Yeah.
So this, yeah.
So can we say that
Right.
for e to the negative x squared, x is 0. So it's like, we can like use separate x's for each product.
Yeah. As long as, again, you use the worst case scenario. And again, that's not the optimal bound, it's a greedy bound. But you can use a greedy bound. It's fine. Mm-hmm.
One big question. Let's say you had an integral of sine squared x, cosine squared x. Now just do 1 over 2, because then it's going to be the sine is going to be 1 over 2 times x minus cosine sine x, cosine x, and then for those
But-
two parts, it'll be 1 over 2.
Oh, yes, that is one way we could do it. I see what you're going at. So you're like this, right? Mm-hmm. And then you do what? That's the integral of 1/4 of 1 minus plus, so minus cosine squared 2x dx, right? Sure. Now there is, some of you see another way to do that, right? I mean, that's not wrong. Not wrong. This is also though sine x cosine x, right? Quantity squared, which you could look at as just sine of 2x over 2 quantity squared, right? So you, in view of that, you can get straight from here down to there. There's always about 3 or 4 different ways to do these. The way you know and understand is the correct way. Hopefully there is a correct way. Let's see here. Oh. Other questions? Comment? No, I won't take comments. I don't want to take comments. That's too dangerous. You know, this material is difficult, but you guys can do it. Just do your best. That's all you can do. Don't stress too much about it. Just work the homework and try to think about how did you do the homework. Yep.
Are we going to get our homework back?
Oh, I sure hope so. Definitely not, obviously not homework 3, but I hope to get homework 1 and 2 back to you Monday. That's my dream. The solutions are posted, of course, right? But I will tell you this, if we don't at least get homework 1 back to you, I will push the test back. So I really hope that doesn't happen. Yep.
You know how in the homework there's questions like find the center of the mass?
Oh, yeah, yeah.
Would that be on the test or?
Those, yes, could be on the test. I would like you to understand the applications of calculus. Now, I would tend to build that into the problem statement. I mean, so, now, the center of mass one, no. I don't really expect you to have that memorized, honestly. But volumes, areas, that I think we can do. Yeah. Wow. Interesting. Only implicitly, I suppose. I mean, you need to know the definition of secant and cosecant and tangent and hyperbolic sine and hyperbolic cosine and the inverse functions. And I mean, so those definitions, yes, implicitly, but there's no like defined continuity in terms of epsilons and deltas. That sort of thing hasn't happened to us. That actually is a very good question for the third test, there will be definitions, and that'll be part of the credit in the test, you know, being able to define limit of a sequence and things like that. But, you know, not this time. Yep.
As far as like kind of questions go, are you gonna be giving us test questions based on like problems that we did for homework, or the stuff that you like told us in access in the lecture, or a bit of both?
Probably a little bit of both. My goal with any test that I give in any course that I teach is really to try to see if you have followed along and if you've understood things as deeply as you can. For this course, that I can pretty much give safe advice, which is to make sure you understand the homework. There's not really much I've done in lecture that hasn't been in homework. There's the main thing, right? So yeah, that would be the one thing that you would want to look at lecture more than homework for, would be the imaginary exponential. That's true. So, good question. So for the imaginary exponential, all you really need to know is what? The cosine and the sine, right? And then just basically the idea, right? If you can work through, for example, how to get the formula for, like, you know, I think a good example to test yourself on is, can you work back out this thing, right? Like cosine of alpha times the sine of beta, something like that. Can you work back out what that is in terms of sums and differences of alpha and beta of sines and cosine? Can you get that with the imaginary exponential technique? If you can do that, you're fine. Pretty much. We did that one day, right? So again, that's, you know, that's about as important to the test as the numerical integration. What is much more important, of course, is rock solid understanding of integration by parts, trig substitution, obviously. Integrals of trig functions are huge. Those are the big ones. So. But yeah, I would say study the homework. I mean, that's probably my best advice, I think. Well, that's all I got for you guys today. So, oh, I'm sorry, I've gone over. No! Look what you guys did to me. How dare you?